Okay, so we looked at, we left off talking about J.J. Thompson, and we had, of course, that sort of big lump of a thing that was the Dalton model. And what Thompson found, was that ray was composed of something that had a negative charge, because he saw that it was repelled by the negative end of a magnet. The other thing that he found was that it had some kind of mass, and that's what we left off talking about, I think. He put the little pinwheel structure inside, fired a cathode ray at it, and lo and behold, the thing moved. Which meant, and you guys all said immediately, well, F equals ma, that meant that if it was accelerating that object in the tube, it had to have some sort of mass. Well, he couldn't measure the mass of an electron, or of this particle that he was finding. But he knew it had to be a physical thing. What he was able to do was get sort of a ratio of mass, and what he found was that it was 1,000 times, 10,000, a lot lighter than a hydrogen atom. So if it's a lot lighter than a hydrogen atom, what's wrong with the Dalton model suddenly? There's the Dalton model, and the simplest atom that's known, and you know, chemists know at that point, because in the 1790s they had done a lot of work with masses, they know that hydrogen is very light. I can't spell hydrogen. They know that hydrogen is very, very light. It's the lightest known element. It's the smallest of whatever this unit is, this Dalton atom. So if you've got something that's lighter than a hydrogen atom, what does that mean automatically?
There's got to be some kind of substance or thing that is smaller than the atom itself.
Yeah. Then it means there has to be some piece that's smaller than that atom. So he must be looking at the first, we talk about subatomic particles, sub meaning smaller than or lower than. So Thompson is the first one to say, you know what, there's more to this. There is a way to divide atoms. There is some unit that is smaller than an atom. Now, Thompson, and a few of you stumbled upon this term, he doesn't call them electrons. Do you remember what he calls them? Some of you had it in your presentations. It sounds very biologically, corpuscles, which is actually, I mean, it's a term that comes out of biological science. Corpuscles are white blood cells, I think, are called corpuscles. I don't know, Moser, you have the degree in biology. What are you looking at me for? But he calls them corpuscles, and they don't get called electrons till later. So how does he square this with what we know about atoms? So what he actually proposes, and I believe I have my dates wrong here. 1897 was when he did a lot of his work. He didn't actually propose the Plum Pudding model until later. But he says that those cathode rays are made up of tiny particles of negative charge. They later get called electrons. He calls them corpuscles. But we know that atoms overall are neutral. So how can they be neutral if we have these little tiny chunks of charge? What he says is that it's like a plum pudding. And Americans have no idea what a plum pudding is. When we think of pudding, we think of like Jell-O pudding packs and like stuff you eat with a spoon. That's exact. And so chemistry students are like, I don't get it. Think of a blueberry muffin. For us, the blueberry muffin model is a better one, or the chocolate chip cookie model. Because a plum pudding is actually this sort of steamed round thing comprised of flour and eggs and sugar and butter and plums and raisins. Yeah, steamed puddings are not everybody's cup of tea. Ha, cup of tea, get it? They're really British, never mind. But if you think about a blueberry muffin, the overall muffin batter, the yellowy stuff, would be your positive matter, and the blueberries would be little chunks of negative. And what he says is they have to be evenly distributed in this mass of positive matter. So it doesn't change Dalton's model really much. I mean, now we know that the atom can be subdivided. But what it adds is that there are these little pockets of opposing charge, and overall the whole thing's neutral. So that is the plum pudding model. So in this new plum pudding model, we have this big thing, and it's all positive except for these little tiny pockets, these little tiny raisins or blueberries or whatever you want to call them, chocolate chips. Great. And did anybody run across the name of the lab at which J.J. Thompson was working? The Cavendish lab. Comes up again and again and again. Basically, working at the Cavendish lab, it seems like for a good stretch of years in the early part of the 20th century, was almost a guaranteed way to get a Nobel Prize, because one Nobel Prize winner after another, after another, after another, came out of working at Cavendish. It was some incredibly bright people. So now that we know that there are these little subatomic particles, these electrons, negative physical particles, and we know that they're much, much smaller than a hydrogen atom. They have a lot less mass than a hydrogen atom. One of the big races that was on was to try to figure out exactly what their mass was. And 1909, Robert Millikan, he's one of the few Americans in this lineup, performs the oil drop experiment, and he gets the exact mass and the exact charge of electrons. And the way he does it, this oil drop apparatus, it's a metal canister, and there's a plate on the top with a hole in it. And they spray oil into that upper chamber. So little particles of oil fall down through the hole. Well, the plate, the hole through which they're falling, has an electrical source hooked up to it. And so they charge the plate. They give the plate a positive charge. And there's a negative charge down here. And they do a couple things. First, they get those drops. So you can, if you know the attractive force on something, and you can get it to fall so that you can measure how long it takes to fall, you can figure out its mass. And that's very basic physics. A student halfway through their first year of college physics could do that. It's pretty simple. Thinking of it is more challenging, thinking of that as a means to measure mass. The other thing that you can do with this setup is once those drops are falling, you can manipulate the charges until you get those drops to suspend midair. Knowing that those drops of oil have an electrical charge, now you can suspend them, and what you can figure out is how big the charge is, how big a charge it takes to get them to suspend, how big an attractive force, and you can actually figure out the charge on the electrons. So he did both mass and charge with this setup. He won a Nobel Prize. I don't think he worked at Cavendish Lab, one of the few. So at this point, after the discovery of the electron, a lot of people were working with the structure of the atom. Once it was kind of known that there was more to it than just that Dalton's, big dull sphere, there were a bunch of people who were making inferences and doing work. So, this idea that there had to be positively charged something for the atom to be electrically neutral, Thomson's answer to that was, well, right, the batter itself, the bready part of the pudding or the muffin or the cookie, the dough, that's all positive. But there were people who were saying, well, what if they're positive particles? The other thing that was starting to be understood was if electrons were that tiny, what gave atoms mass? Why do they have such mass? I mean, we have things like steel, we have lead, we have heavy substances, we have things that are massive. What gives them their mass if this only subatomic particle that we know of is so light? So it kind of sets the race in gear. People are working constantly to try to uncover this. Okay, so my date is, and this gets to one of the things I talked with a lot of you about. I need to go back through and clean up some of my dates, obviously. Rutherford's, well, we call it Rutherford's work. Actually, Geiger and Marsden, who were two of his grad assistants at the, guess what, Cavendish Lab. did most of the work, but it was Rutherford who directed the project. So they did this work in the early part of the 20th century, and it took a number of years of repeating trials and examining every possible angle before they made a proposal. And what they did was they shot alpha particles at thin gold foil. Seems simple enough. The thing about gold is that you can actually, gold is a metal, you know that. It is malleable. What does malleable mean? Very specific meaning. Can be what? That's how we usually use the term, bent or molded, but malleable has a very, very specific meaning in chemistry, which we kind of touch on early when we're talking about metals. It's the ability to be pounded or rolled into very thin sheets. And gold is so malleable that you can make a sheet of gold that is just about 1 atom thick. You can literally make a sheet of gold that is that thin. So alpha particles, many of you came up with this. Alpha particles are just a little, well, they're not little from an atomic view, they're pretty darn big. They're positively charged alpha particles. So it's 2 protons and 2 neutrons. We didn't know that at the time because we didn't know about protons and neutrons. It's basically a helium nucleus. It's a helium stripped of its electrons. And I do need to clean this up. We're fired. So they were fired at this very thin, 1 atom thick sheet of gold foil. And a very tiny percentage of them actually came right straight back. Now that doesn't sound like you sit there and go, oh, okay. The way that Rutherford described this to someone was as if you had shot we very often say, if you had shot a rifle at a piece of tissue paper and the bullet ricocheted. That's how surprising this was. I think he said a shell. This was, of course, the world when he said that, I think it was probably post-World War II, so shells were on the mind. But they were shocked. I mean, they were really, truly shocked. And the weird part was that it was a very tiny percentage of them that bounced like that. We have that sheet of gold foil. We have an alpha emitter, which is some substance that emits alpha particles. So it's a radioactive source. Alpha radiation is one of the 3 types of radiation. It's the least dangerous to humans because it's so heavy. It doesn't penetrate the body's cells very well. You can lay a sheet of paper over an alpha source and block all radiation. You don't need lead shielding for alpha sources. So you've got this alpha source, and it's basically they sort of put it into a container so that all of the alpha particles that were coming out in one direction. So these alpha particles are being shot at the gold foil. And what they expected to see was a few of them go here, a few of them there. The screen behind this was coated with a phosphorescent material so that every time an alpha particle hit the screen, there'd be a little flash of light. And I forget if it was Geiger or Marsden. It was one of his basically graduate students who was charged with sitting in a dark room counting flashes and noting where they struck. And I think later they did develop a better method where they left some sort of permanent mark so that you didn't have to have some poor grad student sitting in a dark room counting flashes. That's what they expected, and they were expecting that based on this idea, that you had this atom, that it's all solidly positive. And if you have something that's solidly positive, if it's completely solidly positive, the positive particles, I suppose, would actually go in and stop. But you've got these little areas of negative spread evenly throughout the atom. So the alpha particles are going to go in, and if they get real close to a negative one, they'll deflect a little bit. But, we assume that a lot of them are pretty much going to go straight through. And a few of them might deflect a little bit. But we're not going to have any real big deflections. It's going to be pretty small. Because that's, that's what would happen if J.J. Thompson is right. You'd get some small deflection. Well, what they found instead, I'll move this up here. And I don't know, this is a question that I've never asked. If originally their screen was all out in front and if they had to sort of change their experimental design. Because what they found was that, while a lot of them did go pretty much straight through, what was it, 1 in 800, I think, went phew, and came right straight back at them. And he said it was as if we had fired a rifle at a sheet of tissue paper and had the bullet come back at you. They were shocked. And one of my favorite, not the one I voted for, but one of my favorites anyway, quotes that was one of the options for the Science Club shirt was something along the lines of, the most useful things in science come not after the moment of, eureka, I found it, but after the moment of, that's weird. That results that are exactly what you expect don't move you anyplace new. Results that are really strange that you have to then understand move you someplace new. So they're seeing like 1 in 800, and they get a few little small scale deflections, but they get, like I said, about 1 in 800 that are either deflected widely or that actually bounce straight back, that come backwards off the foil, as though they were hitting something little and really positive. So what that leads to is this idea, that perhaps, in fact, that region of positive charge is pretty small. And that, in fact, the negative charge is somewhere way outside that region of positive charge. Because what you're seeing is consistent with most of these just passing straight through, unperturbed, and a very few striking something right in the middle. And that's the classic illustration that's done. Because it was about 1 in 800, they assumed that the area of that center was about 1/800th of the area of the atom overall. That's kind of how you come to that number. But that it was tiny, 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 and that all the positive charge was concentrated in this one area. So this leads, and mind you, Rutherford had been J.J. Thompson's student. He had been one of J.J. Thompson's graduate students at one point. He had actually come to England from New Zealand to work in the Cavendish lab with Thompson. So what this leads to is a new model of the atom. And this gets called the planetary model. This is the first planetary model. It does get improved on. It does get improved on. And the planetary model says, well, there's this little teeny, tiny, dense nucleus. And tiny electrons orbit around it like planets. It's just like our solar system. So it's called the planetary model. There are some problems here. There are some issues. But this is the basis of it. And this is Rutherford's atom, where you see these things are all on these little tracks like this, going around it. And it's the one that we very often we use for a lot of logos and stuff when we're talking about the atom. We use this is really the Rutherford's atom. Okay, here's the one hole in Rutherford's model. Mathematically, from a physics perspective, if this is true, these little negative particles should be attracted into the nucleus, and they should just go and get sucked in. Never be heard from again. And then all matter disappears, and we all go off in a puff of smoke, and we're not having this conversation. But clearly that's not how it works. So, and he knew this was an issue. He said, This does not explain why that's happening. So, that's where we'll pick up tomorrow with the person who did explain why that didn't happen and what it took them to get there.